All right, so last time, this is basically where we left off. Okay, we've got our queue. This is just after expanding capacity, we move everything down to the front. We add something, we just follow that fancy thing. Rear equals rear plus 1 mod capacity. I was told that, was it today? I guess today in discrete math. Raise your hand if you're in discrete math right now. Wasn't it fun? Like, what did you learn about today? Did you learn about modular arithmetic?
Yes.
That's kind of funny. That was not planned. But what a happy coincidence. Yeah, so we just do this fancy thing and we can loop back to the front. Cool. So, will this work? Yeah. Whatever, we did this last time. So let's actually have a look at the implementation. So, here's how I'm starting. Why am I doing these attributes? Well, let's see. Okay, default capacity starts at 100. Why? Because, whatever. Capacity, front, rear, count. And then I guess I'm going to want this to be generic. What makes it obvious? Well, you see template class T and the fact that the array, the queue, is of type T. We've got our default constructor. We'll take the constructor that takes the size. Array queue, copy constructor and a deconstructor. We'll have dequeue, in queue. I guess we're going to need expand capacity because we might run out of room, but we know, I mean, we understand the idea behind expand capacity, but of course there's that added complexity with the circular array idea, right? Where we're going to have to like shuffle things a little bit. So we got our dequeue, in queue, expand capacity. First, that's like the same thing as peak again, but for the queue. It is empty in size, great. So let's have a look at the default one. No, that's it. Basically going to be the same as the one that we saw, like it's very, very similar to the array stack, right? We've got our default that I included. Front, 0, rear, 0. Okay, that's going to be new, right? The fact that we've got that. Count, 0, and queue is going to be just the array of type T. Any questions? So far, so good, right? Nothing crazy new. We're just taking all those simple rules and simple ideas that we've been using so far. We're just using those simple rules, again, to create something different. Remember the trick. Don't think too hard. We like to keep it nice and simple. So here's the not default constructor. There. Basically exactly the same. It's just now we pass a size. So, copy constructor. Well, this one's going to be a little hairy. So we're going to copy over all the information from the other object that we're making a copy of. But we got to remember, we got to be careful about like, well, how deep is this copy? Like we don't want it to be too shallow. Well, where do we go? So here's what we're going to do. We're going to create a new array because we can't just make a new pointer point into the same array that we're making a copy of. That's a recipe for disaster. We could do that, but you probably don't want to. So we create a new array. And then what I'm doing is just, well, C is less than count. I guess I'm going to have to be fancy with this capacity thing and copy over all the things in the new queue from the old queue. But of course, based on this, is this a really, really, really deep copy or not? Why not? There's no delete. So that's not, you're right, but that's incorrect motivation is too high.
It is not creating new elements. I mean.
Exactly. T, I don't know what there is in there. They might be pointers to things. So when I make a copy, I could be copying over the pointers to the same objects. But as far as this queue is concerned, that's not the queue's problem. The queue is like, that's the program using the queue's thing to deal with. As far as the queue is concerned, I guess the rule is going to be, well, it might be making copies. Like it might not be that deep, but that's on the user of this queue. Any questions about this? So what am I saying? Take a second to think about the many other possible implementations of this. I mean, I'm starting, I guess I'm saying in the new queue that I'm creating here, get the front plus C plus the mod capacity, okay, and doing the same thing from the other side. This basically means, where did I put my marker? When I'm making a copy, if I have an array that looks like this, whatever, and I've got like like A and B in it, and this is front, this is rear, when I'm making a copy, I'm making it so that the A and the B go in the exact same indices. Do I have to do it that way? Everybody say no. No. I mean, I could have just as easily, this would require me to change some of the stuff up there, but I could have just as easily put it here, right? And of course, I'm going to have like front and rear be correct. But if my copy constructor worked this way, does that really matter at the end of the day if I'm the user of this queue and I'm making the copy? The answer is no. Because as far as I'm concerned, if I'm using this queue, I don't care how it's stored. If it's an array, if it's a link structure, if it's an index, whatever. I don't care. All I care about is that when I dequeue, I get the thing that should be dequeued next. That's what matters. That's it. I don't care. For all I care, we could make a copy and put them here. It's kind of weird to do, but we could do that. Why? Because. Should you? Probably not. That's weird. But you could do it. So the point is, how many ways are there that I could have implemented this? Not only just different ways to code the exact same thing, but coding actually slightly different logic to actually ultimately achieve the same thing. A lot. Deconstructor, I'll just delete the queue. Is it the queue's responsibility to delete the what may or may not be the things in the array? No. That's someone else's responsibility. Okay, now that you're well done, assignment 2. Remember how assignment 2, you had there were a lot of pointers there, but we had maze was a pointer to an array, which contained pointers to arrays, which contained pointers to cells. It's crazy, but that's what it was. What was in the stack? You said cells? Absolutely not. Pointers to cells, yes. There were pointers to cells. Imagine, this is what I did. I got my queue over here. And oh, I'm pushing something on the queue, and it's a pointer to this same cell that's in the maze. Imagine if I pop from this, did I say queue? I meant stack. Whatever. Imagine I pop from this stack. And then, after I dequeued, I delete it or something. Or imagine I'm calling the deconstructor of the stack, similarly for a queue, right? If I delete this and I say, go delete all the things in here, that's going to delete this. But what if the maze isn't done doing what it's doing? What if you're not done with your maze? You just deleted something that was important for something else in your program. Remember that. So, the maze, let's say, is responsible for taking care of its memory stuff. The queue is responsible for dealing with its memory stuff. But the stuff in the queue wasn't the queue's responsibility, or the stack's in this case. Assignment 2. Has anyone started assignment 3? It's a lot of fun, right? A little bit, yeah. When's it due?
16th.
The 16th? Okay. You said a long time? Who said that? Was it someone over here? You're not looking at it? No? It's a long time? Yeah. Maybe there's a reason for that. I don't know. So let's look at our in queue. All right, well, if size is equal to the capacity, we're going to have to expand capacity. Basically, if we're out of room, expand capacity. The number of things in my queue is the same as the number of things that I could put in my queue. I'm therefore out of space, right? So we'll have to expand capacity. We'll see that in a second. Otherwise, queue and location rear is going to be the thing I want to in queue. And then rear, well, we just do that fancy update thing. And we increase the count. Cool. But it's not too crazy, right? It's basically what we were seeing with the stack, except, okay, we've got this circular array thing. Any questions about this, or are we all happy? Getting some nods? Cool. So expand capacity. So let's see what's similar and what's different. Okay, double the capacity, looks good. Create a new array that's of the size of the new capacity. We've got our for loop, but then this is where things start to kind of go a little different. It looks like what I'm doing here is, I guess what I'm doing is that in the new queue, I'm going to go, like, I'm indexing at I. Where is I starting? 0. Where's it going to end? Well, once we get to like the end of like what the count is. But where am I accessing the information from the old queue? Well, we start at whatever the front currently is. The front is going to be, I don't know where. Maybe it's index 7, whatever. So I'm going to start at the front. And then just after that, I just have to update front with the same fancy formula to make sure it loops back. But that's it. So I'm willing to bet when we were starting to think about what's expand capacity going to have to turn into, now that we're complicating it, right? It's going to get hairy. But at the end of the day, I'm willing to bet if you thought it was hairy and you look at this, you think, oh, that's not that bad. All we have to do is take our time. What do we have to do? Well, we need to get the information from the old one, put it into the array in the new spots. But we want to start at 0 here, but here we're not starting at 0, we're starting at whatever the front is. That's it. Just take your time, slow it down. Okay, front. Okay, what comes after front? Front plus 1. Ah, but we might have to move back. Just nice and slow. 0, what comes after 0? Well, 1. I plus plus. And then we update front to 0, rear to count, delete the old queue, and then set queue pointer to be pointing to the new queue. Are we good? Not? Now's the time to ask. It's getting kind of boring just talking at you. I want questions. If you want to ask a question but you're not sure, just ask it.
We are not worried about the rear in the existing queue. We just stop it once it reaches the count. I mean the copy.
Yes, because whatever front is plus count will get us to where the rear really is. So, I mean, I is going to go from 0 to count minus 1, right?
Yeah.
So that means front is going to go from front to front plus the rear, or not rear, like count, which will get us to rear. Good observation though, yeah. Anything else? That's a good question. Okay, yeah.
Comparing to your drawing earlier, you had like a gap and then you had AB. Were you resetting front to 0 there? Like, will that throw like an error if there's nothing actually in that like first index?
Not with the way it's coded. So let's draw that again just to make sure you got what I mean. We have A, B, and then it's twice as big, I guess. So this is front. This is rear, right? The next available spot. When I'm copying over, and of course this is 0, 1, 2, 3. I want to put at 0, what's at front? I want to put at 0 plus 1, what's at front plus 1? And so on and so on and so on until I'm done. So this will become A, this will become B, and then after that's done, like after that loop, that's where I'm saying, okay, front, you're not 1 anymore, you're 0. Rear, you're going to be whatever count is, because that's going to be, right? 2. So 2 is the next available spot. Does that help? Yeah?
Yeah.
Okay. There we go. DQ? Well, what are we going to do if it's empty? I don't know. I'll throw an exception because I don't know what you want to do if you try to DQ from an empty queue. Do you want to crash the program? Do you want the program to keep trying? Do you want the program to ask the user for more input? I have no way to know what you want to do when this happens. So I'll just throw the exception and then it's up to you. Then otherwise, get the result from the front, because that's where it's coming from. Update the front, reduce the count, and return the result. Each nice and simple. Don't think too much. First, we'll just return the thing at the front. We don't have to actually do anything extra fancy other than the exception. But we're not actually removing the front at that time, we're just looking at the front. Size, return count. Is empty, return if count is 0. Yeah, that's it. That's it, that's the array queue. Who here likes the array queue? Who here likes the linked queue? Who here doesn't really care one or the other? What do you think? You haven't put your hand up in any of them. You just don't like any of them? So let's just test it out. So actually, let's not test it out because here's what I could do. Remember the test code for the linked queue? Here's what I'm going to do. I don't have it in the slides, but here's what you could do. Is take that exact same code from the main in the linked queue, but at the very top when it says, oh, create a new linked queue, what do I want you to change? Everybody say, make it an array queue. Ah, that's it. And then you should hit run and everything should work perfectly. Because at the end of the day, I've got a queue. I don't care if it's an array queue or linked queue. I just want to enqueue, dequeue, get the size, and whatnot. That's it. That's awesome, isn't it? Yeah. Any questions about queues before? That's it. We're not talking about queues anymore for a bit. Yes?
If you're interacting with them like basically in the same way, why might you use one implementation over another?
Well, let's say, okay, so this comes down to, I'm going to take your question and generalize it a little bit. Because the question really isn't like, well, why would you pick one over the other? The question really comes down to like, okay, so we've got two different implementations. Why do we care about two? Right? Like, we could implement it this way or that way. And that's kind of the answer to the question is, I mean, I can implement a queue a lot of different ways. At the end of the day, what is a queue? And I was telling people this in office hours. Who here went to Starbucks today? No one? Oh, one person. Well, when you went to Starbucks, did you go into a line?
Yes.
Yes, you did. That line you went into, a queue, if you will, that queue that you entered really is this defined system that we're all familiar with. You've all been using queues. It might seem contrived to think about that line at Starbucks or Tim Hortons or wherever you went this morning. It might seem silly to think of that as like the same idea as this. It is. It's this system, and it has some rules. The rules are, when you enter the back. When you remove it, you leave the front. That's a queue. But how was that queue at Starbucks implemented? Not in C++. It's just people following that idea of the rules of the system. And if we follow the rules of the system, it's going to work a certain way. And it works the way we want for the problem that the queue is solving. First come, first serve at the restaurant. It's silly to think, but it's the same thing. I could implement a queue a billion different ways. The point here is to give you a chance to see multiple implementations. We could compare perhaps computational complexity like we were doing with different implementations. Because here's the thing, we didn't just see 2 implementations, we saw 4. We saw a linked one, and we saw 3 different array ones. And we were talking, oh, what's good about it, what's bad about it? How did it compare to this, how did it compare to that? And in computer science, we love to define these little systems, these sets of rules, and we love to experiment with them. What can we do? What's good about it? What's bad about it? What happens if I change this? Did it get better? Did it get worse? Is it the same? Is it different? These are the things that we get obsessed with. So I'm so happy you asked this question because it's really to emphasize computer science. Don't think about, like it's the idea of the queue, it's not really the implementations that are even really important. It's about here's this system, here's what we can do with it. A stack, that's a completely different system. Here's how it works. You use stacks in real life. Every time you've gone to a restaurant, like a buffet that's got the stack of plates, it's a stack. That system, it's the same idea. We're going to look at other systems. But it's the same idea. We get to play around with these things. I can implement this a bajillion other ways. But at the end of the day, I don't care if it's a linked queue, array queue, a Bob queue. I don't care. All that matters, I don't care if it's a Starbucks queue, a Tim Hortons queue, whatever. All that matters is when you enter that queue, you enter at the end. And when you dequeue, it's going to be the thing that's like at the front. That's it. That's it. That's all that matters. And we're excited about this idea of a queue. So in assignment 2, You didn't even have to implement the stack really, right? Okay, you had to convert it from int pointer to cell. Or you made, did anyone make it generic in assignment 2? No, not a single, that's fine, you didn't have to. In that queue, pardon me, in the stack, like, you didn't implement it because that part really wasn't that important for me on assignment 2. What was important is that you could use that stack. I keep saying queue, I mean stack now. You were using that stack to solve your problem. That's what's important, is this weird idea of a stack, something allows you to do this maze solving. Isn't that cool? And now on assignment 2, you're going to be using a queue, a priority queue, that's going to help you do maze solving. But no, it'll be a different data structure. It'll be a different system that we're using. And you'll notice that the way the maze gets solved is different. It changes when you watch it eventually. You can look at the YouTube videos about how it works and see the difference. One seems to like go down a path and then backtrack, right? And the other one seems to kind of go like, while also kind of like going kind of towards where the exit is as it's spreading out. That was a very long-winded answer to your very simple question, but did that give you a sense of what I care about? Yeah? Other questions? Yeah?
It was just a question about queuing stuff on the array set.
Yeah.
I'm still kind of confused as to the whole like looping around once it actually hits where it, like, what's the word? It goes back and it goes back in front. Like, I'm still a little bit confused as to how it doesn't overwrite when it goes back. Like it's a circle, right?
Okay, yep, I think I know exactly what you're asking, and we're going to do an example right now. Here is my queue. A, B, okay, this is front, okay. Front equals 1, rear equals 0, 1, 2, 3, I guess. Count equals 2. I think that's really all we need right now for keeping track of this. So, I enqueue. And I'm going to go back to the enqueue code. All right? Is size equal to the capacity? I guess capacity. And this, I'm going to make this an, just make this an S for size and C for capacity. Capacity here is 4. Okay? So, I got to enqueue something. Where does it go? You tell me.
The rear.
Goes to rear. Okay, so there. And then what should rear become? So let me put it this way. What rear is 3. What's rear plus 1?
4.
Everybody say 4. But what is 4 mod capacity, which in this case is 4? What's 4 mod 4?
0.
So what should rear become?
0.
Okay, all right, so we'll update rear to be 0. So far, so good.
Yeah.
Good, because I think I know where your issue is. So now, I want to enqueue again. Where should it go? Well, first we have to ask the question, is size equal to capacity? Well, I guess I forgot to increase size. There. Is size equal to capacity? Everybody say no. Absolutely. Did you say yes?
It's false.
False, oh good. So it's not. So we skip that if statement, we don't have to expand capacity. So Q at rear becomes element, well rear is 0, so this is D. Okay, rear is 0. What's 0 plus 1?
1.
1. What's 1 mod 4?
1.
1. Still 1. Okay. Right now, there's nothing wrong with this queue. This queue is safe. It's full in terms of the capacity of the array, but it's still safe. If I dequeue, everything's fine. If I dequeue is removed, front gets updated, size gets reduced, we're fine. But of course, as soon as I enqueue, we're in trouble. Because I'm going to say, what size, 4, is it equal to capacity? True. So this is where I need to expand capacity. So we're not worried about overriding anymore. Because as far as before, this was empty. As soon as we're about to override, nope, we make it bigger, and we just move everything down and start at 0 again. We didn't have to start at 0 again, I guess, but it's nice to do that. There we go. Did that answer your question? Yeah.
So could you also do it where if the front and the rear were pointing at the same thing, then it would expand capacity?
Absolutely, yeah. Because, let me put it this way. What is, okay, the difference between front and rear is going to be the capacity. I guess rear and front. If rear is 10 and front is 5, how many things are in that cube? Like the 5, 6, 7, 8, 9, those things. And then 10 is the next available spot. So at the end of the day, you could, because it's actually all the same stuff, it's just different numbers, keeping track of different things. But absolutely 100% yes. Yeah?
So just to make sure, when you call expand capacity, you make a completely new array and you just copy it.
Bingo, I make a completely new array. So there's 4 things there. I'm going to take A from location front. I'm going to go switch to the expand capacity slide. I take the thing from front in the old queue, which is the A. And where do I put it? In index I, which is 0 in this case. Then B, then C, and then D, and we're good to go. And we update front and rear and whatnot. So this is the front, and this is like this is the line, but see how I kind of just like go like, this goes back there and then copy it over. You like my sound effect? Other questions? This is great. Ask the questions now. Yeah?
Could you explain dequeuing when the queue become empty? Can you show?
Say that again?
Could you explain dequeuing when the queue is empty? I mean.
Okay, so what you mean where we're doing
suppose I had a queue of 2 elements. So for the first time I was able to dequeue it, and at the end of that execution it became empty. So in the linked implementation we had something like front equal to rear.
Right.
So
in the linked implementation, if front and rear are both null,
right.
count is also going to be 0.
Right.
Right? I could do the same thing. Oh, is front and rear the same, therefore it's empty. Or what problem do we have?
Could also be full.
It could also be full. So, but we can check capacity, because capacity keeps track of it.
Okay.
So if I try to dequeue and is empty, that means is capacity equal to 0. Then we know we're empty. And then what do we do if the queue is empty? How do you take something out of that queue? Can't. I don't know what you want to do about that. So everything's going to be fine. In this scenario, if I dequeue, let's see what happens. Ignore this for now. If I dequeue, okay, that's going to happen. Count becomes, I guess size becomes 3, then front becomes 2. For fun. We dequeue again. Front becomes 3, side becomes 2. We're still fine. Do it again. 4, and size becomes 1. Do it again. Okay. That shouldn't have been 4, right? What should that have been? 0. Yeah, there we go. Good. So we do that. Size is 0. Rear.
Is not.
Pardon?
How?
Huh?
I don't know. I don't know.
You don't know? Well, what do we say? Rear was 1. The size is 0. I guess the next, if this is where we just dequeued from, I guess the next available spot still should be the next thing. Even though it could have been moved back, this could have been at any arbitrary point in the array. So I guess it still makes sense. Like, we're okay. But this is where we have a problem. We're going to ask, okay, is it empty? Size is 0. We got to throw an exception because I don't know what you want to do. Other questions? It's a lot of fun. All right. Okay, now we're about to move on to inheritance. So just as a heads up, what I'm about to say, don't think that, oh, this means this is hard or easy. What I'm about to show you is more of like a an engineering thing than like it's not a stack, it's not a queue, right? It's inheritance. This is more of like a programming idea that's pretty cool. You gotta know. So inheritance. So what are we gonna learn? Well, what is inheritance? How to do inheritance? What overriding is, what casting is, although I think a bunch of people already know what this is, and how to use this cool thing called type ID, and really at the end of the day, why we care about inheritance. Is it good, is it bad, whatever. It's pretty cool. So, we have a way to actually derive a new class from an existing one. This is a fairly abstract idea, but we're going to see a couple of examples, and hopefully the dots will get connected nicely. So why do we care? Well, this thing I'm about to show you actually allows us to really easily reuse existing code that are relevant for what we want to do. And it's going to save resources because I don't have to rewrite some code if I'm just reusing some handy code. And it helps organize code logically. We like this logical breakdown of things. But let me put it this way. Let's say I programmed a class called vehicle. What type of attributes might a vehicle have?
Type of cars.
What?
Type of cars.
Well, let's not use that one. What do you say?
Like convertible or coupe.
Yes, but actually this is good because it's kind of emphasizing the point of inheritance. Think of a general vehicle. I don't know if it's a snowmobile or a bus or a car or whatnot. I don't know. If you think about the idea of a vehicle in some way, I mean, I suppose like an airplane and a boat is a vehicle, right? But what is some attribute that a vehicle might have?
Wheels.
How many wheels? I suppose, yeah, that kind of makes sense, right? Maybe boats don't have any, but you can still say 0. What were you going to say?
I was gonna say those, but doors.
Doors? Seems reasonable. These are things we can keep track of, yeah.
Like drivetrain.
What type of drivetrain? Yeah, sure, why not?
They all have some type of.
Yeah. Unless like a canoe. I mean, it might be the boat, I don't know, whatever.
Like gas?
Gas? Yeah, I suppose. Some way to be like, go. Yeah. Yeah.
Seats?
Seats, perfect. I mean, the list goes on. These are all things that like all vehicles could have. But then if I ask you, okay, let's talk about a car. Do we agree that a car is a vehicle? So a car is a vehicle. So all cars are vehicles, right? Are all vehicles cars?
No.
Everybody say no.
No.
Absolutely not. So all cars are vehicles. So that means, based on the attributes we just talked about, like wheels, seats, whatever, cars have those too. But what might a car have that, what were you going to say?
That won't be there. Another type of vehicle.
Like,
I mean, whatever property in vehicle that should be there.
no, so all of them, but what's a property of a car that's perhaps more unique to a car? What were you going to say?
That it's strictly road code.
Like, oh yeah, is it a road going car or like a F1 or something? Right, is that what you're kind of thinking?
No, I was thinking all types of cars strictly go on the road. There's no other.
Well, I mean, they're
Or
kind of not what I'm looking for, but your head's not in the wrong place, don't get me wrong.
automatic.
If it's an automatic car or a standard car, then maybe we can make that argument for vehicle, but I like it for car. What else? What else might be a feature about a car that you don't have for vehicles in general? There's like a bajillion examples. What have you got?
Self-propelled?
If it's self-propelled or requires some sort of like, you gotta push it or something. Sure, why not? Sure, there we go. I mean, we can invent whatever ones we want. But the point is, the information, like the attributes that the vehicle have, and the attributes that the car have, there's gonna be a lot of overlap. But cars, because they're less general, they're more specific, might have some specific attributes. Similarly for buses. A bus is a vehicle, but there might be some specific attributes and functions that you have for a bus that you don't have for vehicles, but all the attributes and functions that a vehicle has, a bus has. And we could keep going down. We could be SUV, smart car, van, school bus, city bus, Greyhound bus, whatever. We could keep doing this and get more specific as we go down. The list does not have to end here. I can keep going on forever. So, wouldn't it be great if I spent like 1 billion years writing my code for a vehicle, and then I want to implement a car, knowing that I'm going to need all the stuff from the vehicle? Wouldn't it be great to be like, okay, you're a vehicle, plus you've got this stuff too, where all I really have to write is the plus stuff? Wouldn't that be cool? That's what the initial designers of this idea thought too. So here's another one. We got shapes. We might have 2D shapes and 3D shapes. And we might have circles, rectangles, and triangles, and then squares, and so on. We can keep doing this forever. I don't know what this click me does, but I'm not going to trust whatever that is. Bank accounts. So let's pretend that we have a class called bank account. And then maybe I want 2 subclasses. I want specialized one, a savings account and a checkings account. Why? Because they're both bank accounts. These 2 new classes are bank accounts. We can inherit and use the information from a bank account when writing a savings account and a checkings account. Because there's going to be a lot of similarity, but maybe some unique specifics. In this example, we would call the bank account the base class. It's the foundational one. And then the other ones we'll call like derived classes, sometimes child class. The one above, sometimes called a parent class, super class. There's a lot of different words that mean the same thing. But in this case, I guess I'm saying base class and derived class. So if we write the class savings account and it inherits from the bank account class, the savings account class inherits all of the attributes and methods from the parent class. It gets them for free. We don't have to write them in at all, assuming they are written in the parent class. But sometimes there are some funny rules about this works. What? I think that's supposed to be how this works. So we'll learn as we go. So I'll look at a couple more examples. I might have a rectangle and a derived class might be a square. And then I might have a student, and maybe the derived classes could be an undergraduate student or a graduate student. Suppose I got like a high school student too. But like if we're talking about a university student, everyone's gonna have a student number. But an undergraduate student and a graduate student they'll have all the things that make them a student, but maybe some specifics that make them unique, specialized. And then a loan, you can have a car loan, student loan, mortgage, whatever. So what do we got? Derived class is called the subclass, or child class, or derived class, although I said that already. The class that the subclass inherits from, parent, superclass, a lot of words kind of mean the same thing. Any questions so far? Are we kind of good? It's fairly high level at this stage. So how do we do it? Well, we'll have a look. So let's look at some code. We'll make a square class and a rectangle class. Are all squares rectangles?
Yes. Yes.
Who said
Yes.
Yes.
Was it you that said no?
I was thinking the other way around.
Okay, let me ask you another question. Are all rectangles squares?
No.
No. Right? So a square is a rectangle. It is. It is a rectangle, but it's a special rectangle. It's a rectangle whose length and width is the same. So all squares are rectangles. But I could have a rectangle that has a length of 5 and a width of 2. It's a rectangle, but is that a square? No, of course not. So we're going to use this example because it's fairly accessible. So let's have a look. So by the way, just to warn you, it's a rectangle. This is the rectangle.h file. It's not generic, so there's no template or anything. We're going back to the nice simple world. I'm just defining the header for my rectangle. And what do we have? A length and a width. Do all squares have a length and width? Yeah, but it's going to be the same. We have constructor, I guess a default constructor, a regular old constructor, copy constructor, rectangle, and we have get length, get width, get area, and the toString. Because why not? I could have more, I guess, but I'm going to keep it nice and simple. Now, does anything in here pop out to you? What the heck is virtual? So this is going to be hard to motivate until we get to the end of the set of slides. So if it's unclear, I'll try to explain it now. I have a feeling it's going to be unclear at the end, so ask me again then. But it's a fancy keyword we can use that kind of enforces us to do certain things. That doesn't make sense. Ask me that question again at the end of talking about inheritance. You'll see. it won't make sense until you kind of know what's going on. Remember, C++ was made by programmers who knew what they wanted to do. It wasn't invented as they went, although it kind of was. Whatever. Never mind. Let's carry on. So let's write a constructor. So a rectangle, they call the default constructor. Let's say it's got a length and width of 0. I guess it's not even really a rectangle at that point, but whatever. There it is. We can have a length and width, width, great. So there's the other constructor where when we call it, we give it the length and the width. Yeah? It's a very simple class. By the way, this is all in the CPP file. It's not in the header. Remember that. Is your hand up? Or you're just our copy constructor, just copy over the length and the width. The deconstructor, there's no fancy memory stuff going on. I'll just create it to shut it up and we're good to go. So far so good. Really simple class, right? I'm not trying to trick you. It is supposed to be simple. Get length, return the length. Get width, return the width. Get the area. I guess this one's kind of fancy, right? Length times width is the area. I suppose we could have made an attribute area that gets calculated automatically, but whatever, let's not. It just calculates it whenever we need it. Any questions about this class so far? Okay, we'll have a toString. I guess my toString, I'm going to say, okay, rectangle, length is whatever the length is, width is whatever the width is, that's it. Any questions? It's nice and simple. We like this. We're going back to weeks ago. Really simple class. By the way, you might remember earlier on in the semester that I was talking about like simple classes and more complex ones. Can you kind of get a sense now what I meant when I say like a stack and a queue are more complex classes than, like it's a collection. It's a lot more complex than just this person object, a rectangle class. Yeah. Any questions? We're good? Okay. So this is all in the CPP file, not in the header because there's no templates generic going on. So rectangle. We just defined a very simple rectangle. That's it. That's how we can visualize it. That's it. We can define a square. Given that a square is a rectangle, all squares are rectangles, right? It's not a crazy thing to say. Let's make our square class inherit from the rectangle class. So this is going to be kind of what we want. And when we do this, the rule is, if we inherit from the rectangle class, the square class inherits everything from the rectangle class. So here's the header. What do we have? I guess we've got no attributes. Oh, weird. But we've got like a default constructor, regular constructor, copy constructor, deconstructor. It's not virtual. What's up with that? I don't know. ToString. I guess what do you notice here that's different? There's two big things. What is different about this versus the rectangle? What do you say?
It's got public rectangle up top.
You've got this funny public rectangle. Yeah, and I guess we're going to have to include the rectangle. Yeah, that's the big one. Yeah, what else?
Nothing in the private.
There's nothing private. That's true, yeah, but that's not what I was looking for. You're absolutely right. What do you think?
There's no virtual there.
There's no virtual. That's another good one, too. More on that in a moment, but that's not what I was going for. I guess I should have said how many differences can you spot. And there's a lot, but there's one I want to, yeah.
You're including rectangle H.
Yeah, so we're doing that, but what else?
Get side. Get side.
What were you going to say?
The square has double S, not double L and double F, W.
Yeah, so there's that. That's absolutely correct, but what did you say?
Get side.
Get side. There was no get side in the rectangle. That didn't exist. We've got this new thing here. So what's interesting is this is an example of we get everything from rectangle, but because it's more specialized, I've added something to it. It's a rectangle, so I get all the facts about that's a rectangle. But because it's a square, I get the side. Right? We'll add that. Why? Well, because, yeah.
Why is the public rectangle up top by itself in its own indented?
I think that's just like the convention that Visual Studio liked me to have. I think it can actually be on the same line, where it says like class square : public rectangle. The public rectangle means we're defining a class called square. Oh, but it's inheriting from a rectangle. So that's where you say, you are a rectangle, but here's what it means to be a square. That's where we say, oh, by the way, you're inheriting. Yeah. Other questions? Okay, I think now is a good time to stop just because I don't want to keep going without, we'll stop in the middle of what we want to know. So yeah, we'll pick up here later. See you Friday. Or tomorrow in lab.